Hello again. I hope you've enjoyed our lectures on the rules of differentiation. Today we're going to see yet another rule, and I think you'll find it fairly easy to use. This is called the chain rule. You'll remember the last few lectures we've talked about the derivatives of sums of functions, sine and cosine, and then we did the product and quotient rules, which gave us the opportunity to find the derivative of all the trigonometric functions. And of course, we noticed that the product and quotient rules are not that easy to use. They're a little messy at times. Now today we'll talk about how to find the derivative of a composition of two functions. Let me show you why that's needed. Consider the following example. We know how to find the derivative of the square root function. That's x to the 1/2. Its derivative would be 1/2 x to the minus 1/2. That's the power rule. But how would you find, say, the derivative of the square root of, say, 3x plus 1? It's a little more complicated inside that square root sign. Well, it's not obvious how to proceed. But notice that this is a composite function. It's composed of two functions. The inside function is 3x plus 1, and then you square root that inside function. In a minute, we'll come back and actually do the derivative of this function once we've developed the chain rule. So how does the chain rule work? Let me explain it with a simple example. I think you'll discover that it's very easy to use the chain rule, but the formal definition of it is actually kind of confusing. So let me show you how it works. Let's do the example x squared plus 1 all cubed. That's a composition of two functions. The inside function is x squared plus 1, and then we cube that inside function. So here's how the chain rule works. Let's find the derivative. The derivative equals, well, it's something cubed. So it's 3 times that thing. So it's 3 times x squared plus 1 squared. In other words, that's like the power rule. But then you have to multiply that by the derivative of the inside function. And the derivative of x squared plus 1 is 2x. So it's 3 times the thing squared times the derivative of the thing, where the thing is the inside function. Isn't that simple? And then you can combine the 2x with the 3 and get a final answer of 6x times x squared plus 1 squared. Now you might say, well, Professor Edwards, I wouldn't have used the chain rule here. I would have just multiplied that cubic out and made it into a long polynomial and then gone boom, 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 differentiating each term of that polynomial. And I say, fine, that's right, that would work. But I'm going to change the problem on you. How about if it's x squared plus 1, not cubed, but to the, say, 100th power? Good luck multiplying that out. Whereas the chain rule would be trivial. It would be 100 times x squared plus 1 to the 99th power times 2x. Simple. Here's the formal definition of the chain rule. And as I said earlier, I find this not very helpful in understanding what the chain rule does. I think it's easier sort of to see it in practice. But let me write this down for you and you can sort of savor it at your leisure. Suppose y is a function, a differentiable function of u. U is that inside function. And u is another function, which is also differentiable. Then the derivative of the composition, dy dx, is the dy du. That's the derivative of the the derivative of the outside function, times du dx, and that du dx is the derivative of the inside function that you add on at the end. If you want to write it in the different notation, the derivative of f of g of x, that's the composition of f with g, is f prime of g of x times the inside derivative g prime of x. Again, I find this definition sometimes not very helpful. Let's do an example to get us sort of comfortable with how to do the chain rule in practice. Let's look at, say, 3x minus 2x squared all to the 5th power, and let's find the derivative. So the inside function is 3x minus 2x squared, and then we're taking that thing to the 5th power. What's the derivative? Well, it's 5 times that thing to the 4th power. That's like the normal power rule. And then you've got to multiply it by the derivative of that inside function, 3x minus 2x squared. So it's 5 times 3x minus 2x squared to the 4th power times the derivative 3 minus 4x. That's that inside derivative. How about that problem we saw a little bit earlier? Square root of 3x plus 1. What's its derivative? Well, first write 3x plus 1 square rooted as an exponent, 3x plus 1 to the 1/2 power. And then use the chain rule. It will be 1/2, bring down the exponent, times 3x plus 1 to the minus 1/2, and then don't forget the inside derivative, which in this case is just 3. So the final answer is 3 over 2, and of course 3x plus 1 to the minus 1/2 is the square root of 3x plus 1 down in the denominator. Notice the form of both of these problems that we just did are of the form something to a power, u, which is the inside function, to a power. This is often called the general power rule when we apply the chain rule to u to the n. And the derivative of u to the n, where n is any real number, is n times u to the n minus 1, and then don't forget the derivative of the inside, du dx. So it's kind of like the power rule. Remember how the power rule worked, except now you've got, instead of having x, you've got some bigger quantity, some function of x, so you multiply at the end by the derivative of that larger quantity involving x. So the chain rule has this special case of the general power rule. The chain rule is actually more general. For example, if you want to define the derivative of sine of 6x, that's not a power rule problem. That is actually just a straight chain rule. Let's do it. What's the derivative of sine of the quantity 6x? Well, here's how I talk about it. I would say this is sine of something. So the derivative of sine of something is cosine of that thing. And then I have to differentiate that thing. I have to do the inside derivative. So an extra 6 plops out. And the final answer is 6 cosine 6x. Nice, isn't it? Not so bad, I don't think. Let's do a monster example, a much bigger example that combines a number of skills. See if you can follow along with this one and see all the steps that we're doing. This is kind of get our hands dirty here a little bit. Let's consider the function x squared times the square root of 5 minus x squared, and let's ask the following question. What's the derivative of this function at the point 1, 2? In other words, imagine the graph, and we're trying to find the slope of the tangent line on that graph when x equals 1. That's what we're trying to find. Well, here we go. We take the derivative, and I hope you notice the first thing is, this is a product rule, isn't it? It's one function, x squared, times another function, that's square root. So we have to do the product rule first. So here we go. Before I do the product rule, of course, I want to make sure that I rewrite the square root of 5 minus x squared as an exponent, 5 minus x squared to the 1/2 power. So what's the product rule do? It's the first times the derivative of the second. Well, the derivative of that second function requires the chain rule. Wow, what a neat problem this is. It has a product rule and an embedded chain rule. So here we go. It's x squared, and now I'm going to differentiate 5 minus x squared to the 1/2 power. That's 1/2 5 minus x squared to the minus 1/2 times the inside derivative, which is minus 2x, plus the second term, 5 minus x squared to the 1/2, and the derivative of the first term, oh, thank goodness, that's pretty easy, just 2x. And then we could simplify this, but because we want the derivative at a particular point, go ahead and plug that point in right now after you've differentiated. And this is actually non-trivial to plug in 1. Watch what happens. The x squared is just 1. There's a 1/2, and then there's a 4. 5 minus 1 is 4 to the minus 1/2 times the minus 2 plus, and the second term is 4 to the 1/2 times 2. Add those together. Wow, well, what's 4 to the minus 1/2? That's 1 over 4 to the 1/2, which is the square root of 4. So that's 1/2 times 1/2 times minus 2. That gives a minus 1/2, and the second term gives a 4. Add those up, 7/2. Ouch. That sure was a lot of pre-calculus. And I've said it over and over, and it's really true. There's a lot of algebra here that we have to be sort of comfortable with. I invite you again to practice this problem maybe at your leisure, and then in the workbook you'll see other problems like this that will not only have a derivative calculation, but they'll have some pre-calculus afterwards. It's not pleasant work, but we have to be pretty good at it. Let me pause here and give some study tips. Many of these we've talked about before. If they ask for a derivative at a point, plug that point in right after you take the derivative. Don't simplify ahead of time. On AP tests, remember, you don't really have to simplify your answers, but in college, you may have to ask your professor. They may require simplifications. And then again, remember that the back of the book answer might not look like your answer, but you still could be correct. Let's do another chain rule problem that has a nice little twist to it in that it's a double chain rule. Let's find the derivative of sine cubed of 4x. By the way, notice this notation, sine cubed. That means the sine function all cubed. We tend to write that cube after the word sine instead of outside. So it really means sine of 4x all cubed. What's the derivative? Well, the chain rule would say it's 3 times the function sine 4x squared times the derivative of sine 4x times the inside derivative. But wow, that itself requires a chain rule, doesn't it? That itself is a composition. So our answer now is 3 sine 4x quantity squared times the derivative of sine 4x, which is cosine 4x, times the inside derivative, 4. Wow. Double chain rule. And then simplify all this mess, and you get 12 sine squared 4x times cosine 4x. Pretty tough going. Let's do a surprise problem. Let's find the derivative of sine squared x plus cosine squared x. Let's see what happens. So what's the derivative of sine squared? Well, that's something squared. The derivative would be 2 times sine x times the derivative of sine x, which is cosine x. Plus, what's the derivative of cosine squared? Well, that would be 2 times cosine times the derivative of cosine, which is minus the sine. So look at our answer. The derivative is 2 sine cosine minus 2 cosine sine. That equals 0. Wowee. The derivative of my original function is 0. Quite curious. Why is it 0? Do you see what's going on here? Ah, yes. Sine squared plus cosine squared is equal to 1. That's that famous trig identity. So you would expect its derivative to be 0. In fact, you might have said that in the first place and said, why do the chain rule? I know it's equal to 1. The derivative must be 0. Let's do a similar problem. Let's find the derivative of tangent squared minus secant squared. Here we go. The derivative of tangent squared is 2 times tangent times the derivative of tangent. Memorize, memorize. Oh, that's secant squared. And then I have to differentiate secant squared, which is 2 secant, and then the derivative of secant, which is secant tangent. And now look at our answer. It's 2 tangent secant squared minus 2 secant squared tangent. That's 0. We got 0 again. That ugly looking function, sort of complicated, has a derivative equal to 0. What's going on? Well, let me show you. Remember our identity, sine squared plus cosine squared equals 1. This identity, if you divide both sides by cosine squared, gives rise to another very important trig identity. So take sine squared plus cosine squared equal to 1 and divide both sides by cosine squared. The first term becomes sine squared over cosine squared, which is tangent squared. Cosine squared over cosine squared is 1, and the other side is 1 over cosine squared, which is secant squared. Now look back at our original problem. It was tangent squared minus secant squared, wasn't it? Well, according to this identity from trigonometry, that's a constant. It's equal to minus 1, and we would expect its derivative to indeed be 0. By the way, please memorize that trig identity, tangent squared plus 1 equals secant squared. I say that even though you can derive it by the trick I just showed you. Let's find the second derivative of a particular function. How about 1 over 2x minus 6? Let's practice doing differentiation twice. So this can be rewritten as 2x minus 6 to the minus 1 power, and now I do the chain rule. The derivative equals minus 1, 2x minus 6 to the minus 2 power, times the inside derivative 2, and then I simplify. That's minus 2 times 2x minus 6 to the minus 2 power. Now differentiate it again. So I get the second derivative equals. Well, first there's the minus 2 I had sitting in front originally, and then I bring down the exponent that gives me another minus 2, and then I get 2x minus 6 to the minus 3, and then another inside derivative 2. Boy, there are a lot of 2's floating around here, and if you simplify all those 2's, it turns out to be the minuses cancel. You get 8 divided by 2x minus 6 all cubed. Good, good. That was a pretty hard problem. Let's turn now to an application of what we've been doing with the chain rule. I'd like to look at a pendulum problem. These kind of problems occur a lot in physics. Imagine you have a pendulum hanging from the ceiling, and it's 15 centimeters long, and it moves according to the equation that its angle is equal to 0.2 times cosine 8t, where t is time, and the angle, of course, is measured in radians. Here's a picture of that pendulum, and it makes an angle theta, and it kind of goes back and forth, according to that equation. Well, we know the position function. Let's calculate the maximum angular displacement. In other words, how far out does the pendulum go before it swings back? And also, let's calculate how fast the pendulum's moving, its angular velocity with respect to time. Before we do that, let's study some of the values of this function for various values of t. For instance, if t is 0, then cosine of 8 times 0 is just cosine of 0, which is 1, and so theta is 0.2. That turns out to be the maximum displacement because cosine at most is equal to 1. So at time 0, this thing is out here at maximum angle 0.2 radians, and then it swings back over to minus 0.2 radians. Notice that when t is pi over 16, you get cosine 8 times pi over 16, which is cosine of pi over 2, which is 0. And hence, at pi over 16, the pendulum is vertical, and then it keeps swinging over. So let's complete the problem. Here's the formula. Theta is 0.2 times cosine 8t. The maximum displacement, as we said earlier, is 0.2 radians. That's because that's how big cosine can get. And the derivative is, by the chain rule, 0.2 times minus sine of 8t, and then the inside derivative is 8. So it's minus 1.6 sine of 8t. Notice that when t equals 0, the rate of change of the angle is minus 1.6 times 0. What does that mean? When time is 0, remember the pendulum was out here at its maximum displacement, and it's actually not moving. It's coming out, and then it turns around. That's why d theta dt is 0 there. It's slowed down, and then it turns back around and swings back. Kind of a neat problem, and I invite you to plug in some other t values to see how this behaves. Okay, good. I'd like to look at a problem now that actually will be looked at again next time when we talk about a topic called implicit differentiation. I'm going to look at the problem here from the viewpoint of the chain rule and show some of the flaws of this problem, or our approach to the problem, and then we'll see a better way to do it next time. So what I'd like to do is analyze the circle x squared plus y squared equals 25. That's a circle of radius 5. And I want to find dy dx, the derivative, or the slope, at any point on the circle. Here's how you might do that. Take the y squared term and leave it on the left, and bring the x squared to the other side, and then take the square root of both sides. So you have y equals square root 25 minus x squared. Now there's a flaw with this. We're assuming here that y is positive, aren't we? If we wanted to know the slope at a negative value of y, this wouldn't quite work. So let's assume for the moment that we're going to deal with the upper hemisphere. So I want to find the slope, so I'm going to have to differentiate this function, square root 25 minus x squared. So I write it as an exponent, 25 minus x squared all to the 1/2 power, and I use our old friend, the chain rule. 1/2, 25 minus x squared to the minus 1/2 times the inside derivative, which is minus 2x, and then I simplify this and get the 2's to cancel, and it's minus x over the square root 25 minus x squared. And again, this is the derivative at any point above the y-axis, above the x-axis. We're in the upper semicircle as indicated in this figure, because the square root is always going to be positive. So what kind of derivatives can we now calculate with our formula? The derivative is minus x over square root 25 minus x squared. That's telling me the slope of this semicircle at various points. We're going back to kind of basic principles here. Let's make sure we're comfortable. 3, 4 is on that circle. It's on that semicircle. What's the slope there? Well, you would plug 3 into the equation. Look how it works. The denominator would be 25 minus 9, 3 squared, and the square root of 16 is 4, so it would be minus 3/4. So at 3, 4, the slope's negative. At minus 3, 4, the slope turns out to be positive. How about at 0, 5? How about if x is 0? Well, the numerator is then 0, and the slope is 0. And how about at 5, 0? Well, if you plug in 5, you're dividing by 0, aren't you? So the slope's undefined at 5, 0. Let's look back at our picture and see how these results are verified geometrically. Look at 3, 4, the slope is negative. At minus 3, 4, the slope is positive. Up there at 0, 5, you have a horizontal tangent. The derivative is 0. And then back down at 5, you can see that actually the curve has a vertical tangent, doesn't it? And the derivative is not defined there. Great. Good going. We'll come back to that problem next time. Let's do a pretty hard problem now. Let's find the points on the interval 0, 2 pi at which this function has horizontal tangents. Finding points where functions have horizontal tangents is an important skill in applied calculus. So we're going to do this problem, and this will give rise to some interesting trigonometry. So what do? We take our function, 2 cosine x plus sine 2x, and we take its derivative. I like to always tell students, when you don't know how to start a problem, when in doubt, take a derivative. You'll get some partial credit. So we take the derivative, and we want to set it equal to 0 to find where the derivative is 0, and we already have a problem. That's a hard equation to solve. But let me remind you of a trig identity. Remember that cosine 2x is equal to cosine squared minus sine squared, or 2 cosine squared minus 1, or 1 minus 2 sine squared x. That's one of the fundamental trig identities. I haven't talked about it yet in this course, but it is part of that review lesson that we did back in lesson 3, and you'll see it in our workbook. So I can replace cosine 2x with 1 minus 2 sine squared x, and then I'll have an equation just involving the sine function. Also, by the way, I can, of course, cancel the 2's in the derivative equation because they're no problem. So we take our equation, sine x minus cosine 2x, replace cosine 2x with 1 minus 2 sine squared x, and then we have an equation involving just the sine function, 2 sine squared x plus sine x minus 1 equals 0. Wow, well, that's a polynomial in the variable sine x. You can factor that. It's 2 sine x minus 1 times the quantity sine x plus 1. Check yourself, multiply out that factored form, and you'll get the original problem. And now, the factored form is equal to 0, so either term can be 0. If sine x is equal to 0, if the first term is equal to 0, that means that sine x is 1/2. That would make the first term 0. And in that case, x turns out to be pi over 6 or 5 pi over 6. If the second term is 0, that would mean that sine x is minus 1, and that occurs when x is 3 pi over 2. Notice how we have to be very, very comfortable with solving trig equations like I did back in lecture 3. Being comfortable with trig is a key aspect of success in calculus. Here's a picture of that original function, which verifies the results we just had. Notice that at pi over 6, 5 pi over 6, and at 3 pi over 2, the function has a horizontal tangent line, doesn't it? It's kind of neat how the picture verifies the analytic work that was so difficult to do. Let's do a practice problem. Let's see if you can do the following problem. Can you find the derivative of 3x plus 5 to the 50th power? Think about that. How would you find the derivative of 3x plus 5 to the 50th? This is now back to our original discussion of the chain rule. Hopefully, after this lecture, you look at that problem and go, ha, that's easy, I can do that one. It's nothing more than 50 times 3x plus 5 to the 49th, and then don't forget the inside derivative times 3. Good. And then you could, of course, simplify that. Great. I think you're comfortable now with the chain rule. So what are we going to do next time? We have one more lecture on formulas for derivatives. And next time we're going to look at a topic called implicit differentiation. This will allow us to look back at that circle. Remember, x squared plus y squared equals 25? We'll be able to attack that problem in a much more global fashion and not have to just restrict to the upper semicircle. Again, I think you'll find implicit differentiation a fairly straightforward topic. When we finish with implicit differentiation, we'll basically have all the derivative rules we'll ever need to be successful in calculus. Now, that said, we're going to have some more functions come into play. We're going to have logarithmic functions and exponential functions and things. But these rules are fundamental, and they will serve us well throughout the course. We'll also see some really neat applications next time, something that we call in mathematics related rate problems. And I'll leave you with the following kind of puzzle. Suppose you have a circle whose radius is increasing at a certain rate. How would you calculate how fast the area of that circle is increasing? So it's the related rate of growth. The radius is growing. How is the area growing? So thank you very much, and I'll see you next time.